Hello, my name's Alan Kennedy, and in this screencast we're going to look at RL circuits. The circuit shown is a series parallel RL circuit, and we are going to analyse this circuit by calculating the current through each component. To do this, we must first calculate the total circuit impedance, which we will use to calculate the total circuit current. We will begin by first simplifying the series section of the circuit so that we are left with one resistor value and one inductor value. Resistors R1 and R2 are in series, so they can be added together, giving a resistance of 40 ohms, which we will call R series, the series resistance. Inductor L1 is in series with L2, so they can also be added together. These two series inductors are in parallel with inductor L3, giving us a total series inductance of 20 millihenry. We will also simplify the parallel section with the total parallel resistance calculated by adding resistors R3 and R4 as they are in series. This gives us a total parallel resistance of 100 ohms. We will call this resistance R parallel. The total parallel inductance is then calculated by calculating the inductance of L4 and L5 in parallel, which gives us 16 millihenry. Simplifying the series and parallel sections gives us the following circuit. Next, we will calculate the inductive reactance for the series and parallel inductors. This works out to be 126 ohms and 101 ohms. We then calculate the impedance and phase angle of the parallel section, as we need to convert the parallel resistance and inductance to their equivalent series values in order to calculate the total impedance. The impedance and phase angle of the parallel section are needed to do this, and they work out to be 71 ohms and 45 degrees. The equivalent series resistance and inductive reactance is calculated as shown, with R equivalent and XL equivalent both working out to be 50 ohms in this case. RS and R equivalent can then be added together to give us the total resistance. The series inductive reactance and equivalent inductive reactance can also be added together, giving us XL total. We can now calculate the total circuit impedance, which works out to be 198 ohms, and the total circuit current, which works out to be 30.3 milliamps. The final step involves using the current divider formula to calculate the current flowing through each component. The total current will flow through R1 and then reach a junction where it will be split into two paths. This means IR1 will equal 30.3 milliamps. The first of these two paths will direct some of the current through L1 and L2, while the second path will direct the remainder of the current through L3. The current divider formula can be used to calculate how much current flows through each path. The impedance of each branch and the total impedance of the parallel section must be calculated so that the current divider formula can be used. The impedance of the top branch, which we will call XLA, works out to be 251 ohms, as does the impedance of the bottom branch, which we will call XLB. The impedance of this parallel section was worked out earlier as XL series, the series inductive reactance, and it is 126 ohms. The current divider formula can now be used to calculate IL1 and IL2 and IL3, with all three currents working out to be 15.2 milliamps. The current through each branch should add up to the total current flowing into the junction. The current through the two branches add up to 30.4 milliamps, which is slightly higher than the 30.3 milliamps of current flowing into the junction. This difference is due to rounding off errors. The current through each path joins together again to become I total, which flows through resistor R2. This means that IR2 equals 30.3 milliamps. The total current will flow through R2 and then split into three paths. The first path will direct some of the current through inductor L4. The second path will direct some of the current through resistors R3 and R4, while the third path will direct the remainder of the current through inductor L5. The current divider formula must be again used to calculate how much current flows through each path, with the impedance of each branch and the entire impedance of this parallel section needed. The impedance of the branches work out to be 126 ohms, 100 ohms and 503 ohms. We worked out the impedance of the resistive branch earlier as R parallel. The total impedance of this parallel section was also worked out earlier as Z parallel, and it works out to be 71 ohms. Using the current divider formula, we calculate IL4 to be 17.1 milliamps. IR3 and IR4 will be equal to 21.5 milliamps, and IL5 will work out to be 4.3 milliamps. It is worth noting that the currents flowing through the three branches will not add up to I total when added together. This is because the current through the resistive branch is 90 degrees out of phase with the current through the inductive branches. IT will equal the square root of the current through the resistive branch squared plus the current through the inductive branches squared. And that is the end of this screencast.